Very good evening, my dear students. In this video lecture, I am going to present you Fourier series. I request you all to listen to the video lecture and come for your CAT 2 examination. I have told you in the class, because of the lack of time, we are studying this topic using a video lecture. This PPT and another material for Fourier series will be uploaded in Moodle. Please download that and study from that also. Okay, let us start. The Fourier analysis tools are of two types: Fourier series and Fourier transform. These two are the most important mathematical tools which are used for the analysis of signals and also used for the design of LTE systems. These Fourier tools are said to identify the frequency content of a signal. When you see a signal in the time domain, you may not be able to see the frequency content of the signal very directly. But when you do the Fourier transform, okay, for the signal and view it from the frequency domain, you will be very clearly seeing the frequencies which are present in the signals and also the amplitudes of the signals. And if you take the phase spectrum, you will be able to see the phase of the signal also. So this is how this Fourier tools are called as analysis tools. Like a prism, okay, when a white light falls on it disperses into different colors and you will be able to see all the colors, all the spectrum, or all the various colors in the white light. Similar to this, when you give a signal to a Fourier transform tool or into a Fourier tool like Fourier transform or Fourier series, you will be very clearly able to see the frequency content of the signal. Okay, so this is how it is very useful in signal analysis and in all the types of signal processing applications. These tools basically involve the decomposition of the signal in terms of sinusoids, that is, or a complex exponential signal. Okay, so you may be using sine waves and cosine waves, sum of sine waves and cosine waves, or you may be directly using a complex exponential signal. So this is the base function for Fourier transform. Fourier tools, Fourier transform as well as Fourier series. The decomposed signals are said to be represented in the frequency domain. Okay, so the Fourier series is used for periodic signals, whereas Fourier transform is used for aperiodic signal. Okay, so you know that basically you have two types of signal, periodic and aperiodic signal. So if a signal is periodic, Fourier series will be more suitable for expressing it in the frequency domain. And if a signal is aperiodic, you will be using the tool called as Fourier transform. Fourier series, what it does, it breaks down the periodic function into weighted sum of sinusoidal functions. Okay, you can also call this as the Fourier transform for a periodic function. Okay, so Fourier series, it will write a periodic signal in the form of weighted sum of sinusoidal functions. Okay, the periodic function may be anything. It need not be a sinusoidal signal. It can be anything of any shape, but you will be able to express it in the form of weighted sum of sinusoidal functions. Similarly, okay, in the other way, the Fourier transform is used to represent an aperiodic signal in the frequency domain. Okay, and the spectrum of an aperiodic signal will be continuous, whereas the spectrum of a periodic signal will be a line spectra, that is, it will be discontinuous. Okay, now let us see few things about Fourier. Okay, his full name is Jean-Baptiste Fourier. He belongs to the 18th century and he is a French mathematician, and his contributions are very important to mathematics and physics. And what he does is, he claimed he was actually doing some research work on heat propagation. Okay, and the heat propagation of the earth, actually he was working on the ground for the agriculture as well as for different applications. He was working with Napoleon, and he's a scientist and he is a government official. You can read his history anywhere from Google. Okay, so his contributions are very important and very useful for the field of signal processing. Okay, digital signal processing and image processing everywhere. That's why we remember Fourier so long, and that's why we talk about Fourier before you study about Fourier series or Fourier transform. So what he does is, he claimed that any function of a variable, whether it is continuous or discontinuous, can be expanded in a series of harmonically related sines and cosines or complex exponentials. Okay, so he claimed that any function, if it is periodic, okay, if it is periodic or even if it is aperiodic, he has an alternate. So it can be expanded as harmonically related sinusoids. And for aperiodic signals, he obtained an expression not as a sum of sinusoids, but as a weighted integral of sinusoids that are not at all harmonically related. So for aperiodic signals, he is able to express it as an integral. Okay, whereas for periodic signal, he is able to express it as sum of harmonically related. That is, if the fundamental frequency is omega, you will be having the other sinusoids which will have a frequency 2 omega, 3 omega, 4 omega and so on, and they will be weighted. That is, there will be a coefficient which will be multiplying the sine function or cosine function or the complex exponential function. Okay, so this is what he proposed for a periodic signal. And for aperiodic signal, instead of sum, you have to integral. You have an integral of sinusoids, and they need not be harmonically related. Okay, so he was actually a student of great mathematicians like Lagrange, Laplace, and these scholars or these scientists, they did not approve his paper, Fourier's paper, which was written in 1807, and it was not accepted. Lagrange was, very much against his paper, and it was not at all accepted. And during the end of his life and after the death of Lagrange only, excuse me, and this his paper, okay, which proposed this Fourier series and Fourier transform was accepted, and then only it was published. So from 1807 he proposed this, but it was published after 1878, okay, in English. Okay, he wrote it in French. So his finally they found that his observations are correct with additional conditions. So Fourier's observation that discontinuous functions are sum of infinite series was a breakthrough, and we call it as Fourier series. Okay, I doubt whether you can appreciate this discontinuous function, this term discontinuous function. Okay, because here we are having sum of sinusoids where sine wave and cosine waves are continuous functions. Okay, they are periodic and they are continuous functions. But even if you have a square wave where you have discontinuity, where you square wave or any other wave which has discontinuity, which are not having smooth edges, they can also be expressed as sum of sinusoids. This is his proposal, or this is his finding. Okay, and now this was a breakthrough, and we call it as Fourier series. Okay, let us see more. And in mathematics, infinite series are very important. Okay, so they are extensively used for in calculators and computers for evaluating the values of many functions. You have studied many Fourier series, Taylor series, and other series. Fourier series is a way of representing a periodic function or a periodic signal as an infinite sum of sine and cosine functions. Okay, as we have already seen, it is analogous to a Taylor series, which represents function possibly as an infinite sum of monomial terms. Okay, polynomials. You write it in terms of polynomials in a Taylor series, but here you use sine wave and cosine wave forms. Okay, so and for functions which are not periodic, the Fourier series is replaced by Fourier transform. So he has an alternate for a aperiodic signal also. Even signals with sharp edges like square wave or sawtooth waveform can be perfectly expressed using Fourier series. Okay, so this is the breakthrough, or this is the difference. Okay, now I said that there are some conditions for the Fourier series to exist. That is the conditions that we are able to write a periodic function in terms of Fourier series, and these conditions are called as Dirichlet conditions. Okay, Dirichlet conditions, and the conditions are three. So a periodic signal has a Fourier series if it satisfies the following conditions. Number one, okay, x of t is absolutely integrable over any period. Okay, it is a periodic signal, so it has a period t. So if it is absolutely integrable over one period, okay, that is if the integration is less than infinity, then you can express it using Fourier series. And okay, these all the conditions must be satisfied. And then if x of t has what is it, only finite number of maxima and minima in any period, that is within a period it cannot go up and down. Okay, you cannot have so many maxima and minima, you can have finite number of maxima and minima within a period. And then it has finite number of discontinuities over a period. Discontinuities means there is a step that is from 0 to 1, or from -1 to +1, or from some value. There are some discrete, it is like a discrete, from one value it jumps to another value. So these there is no it is not a smooth change in the amplitude, but there is a discontinuous change in the amplitude. So the number of discontinuities must be finite over any period. Okay, so these three conditions are called as the conditions for the existence of Fourier series. Okay, now let us see an interesting example for Fourier series, imagination for Fourier series. So all of you would have gone to seashore and see the would have seen the waves. Okay, waves, how the waves are forming, and from inside the sea waves will be coming, and okay, everyone would have watched it, observed it carefully. So now the waves of the ocean consist of actually linear combination of sinusoidal waves. Now if you visualize, you can see the waves coming, and all the waves are sinusoidal in shape, right? You can see all the waves as sinusoidal waves. Okay, sine waves or cosine waves of different magnitude and different frequencies and different phases with respect to each other, and so on. Okay, so now when all these sinusoids overlap, okay, or few sinusoids, when few sinusoids overlap, it will form a wave which comes and touches the shore. Okay, so the one which comes to the shore, or which touches the ship, will be a combination of, it will be a linear combination of sinusoids of different frequencies, that is different wavelengths, and different heights, that is different amplitudes. Okay, so here in the diagram you can see three what is it, waves, sinusoidal waves of different wavelength. 150 feet, okay, that is the wavelength, or the spatial period. Okay, wavelength is 150 feet, 500 feet, and 800 feet, and their amplitudes are also different. Okay, and their amplitudes are also different, and when they superimpose on each other, okay, at a particular phase, you get a wave which comes to around 100 feet height. It may go up to 198 feet height depending on the phase. Okay, so this is how they superimpose. These superimpose means they are summated. Okay, they are added to get another waveform. So all these waves which are being produced are linear combination of other waves. So this is these waves are also sinusoidal in shape, and the resultant wave is also sinusoidal in shape. Okay, in the ocean. Now let us see another example, how you can form a square wave from sinusoidal wave. So this is the speciality of Fourier series, that is any periodic signal of any shape, it need not be related to sinusoid at all. Okay, a sine wave at all. It can be anything. It can be a square wave, it can be a rectangular wave, it can be a sawtooth wave. Okay, it can be elliptical shape, and so on, but it should be periodic. Okay, so these can be written in terms of sinusoids. Now let us see how you are forming how we are going to nearly we are getting a square wave from sine wave. So the first sine wave is of frequency sine 1/4. Okay, 2.5 is the amplitude. It is a DC value. We don't have any sine over there. Sine here 2.5 is the DC value, or the average value of this signal. and then 10 by 4 is the amplitude of the particular sine wave. Okay, and then you have sine 1 by 4 pi t. So 1 by, it is sine omega t is the what is it, general form. So omega is 1 by 4 pi. Okay, so it will get you a t, or it will give you a frequency, okay, a particular frequency. And now it is being, what is it, added with another sinusoidal wave, sine wave. Okay, sinusoidal wave, we don't know whether it is sine or cos, sinusoid. Okay, of amplitude 10 by 3 pi and a different frequency. Okay, instead of 1 by 4 you are having now 3 by 4 pi. Okay, so it is 3 times, this frequency is 3 times compared with this waveform. This frequency is 3 times. Okay, so when you add these two, you get another signal, again periodic signal. Okay, these two are periodic, and when you add these two, you get another periodic signal which looks like this. And now this result plus another waveform. Okay, another waveform, its amplitude is 2 by pi, and it's what is it, it's uh, frequencies 5 times when compared with this. Here it is 1 by 4 pi. Now it is 5 into 1 by 4 pi. So this is 5 times the frequency. So this is called as harmonically related sinusoid. Okay, that is, first you have a sinusoidal wave, and then the next frequency is multiplied by a factor, again multiplied by another factor. So with respect to the fundamental frequency, the other waveforms are harmonically related. Okay, they are harmonics, and the amplitude is also different. That's what it is called as weighted sum of. Okay, here the weight is weight, the amplitude also differs. Now this gives you this, and then the previous result plus another waveform gives you this, the previous result plus another waveform gives you this. So when you compare with the first waveform, okay, and this waveform and this waveform, you are coming nearing to a square wave. Okay, this doesn't stop. You can go on adding. For a square wave you can have so many terms. It is actually, it can have infinite times to get a perfect square, or you can stop with a few terms to get almost a square. Okay, so when you add more number of waveforms to this, you will be getting a perfect square wave. Okay, so you can, that's what it is said, that you can express square wave in terms of sine waves. Okay, of what is that, a sum of, what is it, weighted sum of harmonically related sinusoids. Okay, now I hope you understand what is meant by weighted sum of harmonically related sinusoids. They are all sinusoidal waves. Their frequency is related by a multiple, by a integral multiple. Okay, so with respect to the fundamental frequency, it is multiplied by a integer. So they are harmonically related, and the amplitude is different. So you are getting a weighted sum of harmonically related sinusoids to get a square wave. Okay, okay, now let us come to the formula. There are different what is it, different forms, or what do you say, different Fourier series, a trigonometric Fourier series, exponential Fourier series, cosine form, different forms of Fourier series, let me say. Okay, so trigonometric form, exponential form, cosine form, sine form, and so on. So in our lecture we'll see two forms, trigonometric Fourier series and exponential Fourier series. Okay, the others we can leave. It is easy if you, but it is not there in our syllabus. We limit our discussions to these two. Okay, so now in trigonometric Fourier series, you will have both sine terms and cos terms. Okay, sine waveforms and cos waveforms. So this series is given in terms of sine and cosine terms, and it is known as trigonometric Fourier series, and is given as below. So x of t, this is the synthesis equation, that is x of t is the periodic waveform what you are writing, and it can be written in form of Fourier series. Okay, that is the formula. So that is the Fourier series form, a naught plus summation n is equal to 1 to infinity a n cos n omega naught t plus bn sin n omega naught t. Okay, so you will have from n is equal to 1 to infinity, infinite number of times, and then you will be having cos terms multiplied by a coefficient called as an, and sine terms multiplied by a coefficient called as bn, and the sine and cosine waveforms are of different frequencies which are given by n into omega naught. Okay, so as n varies from 1 to infinity, you will be having the different harmonics. Okay, a naught is the DC value, or the average. It will give you the average amplitude of your periodic signal. Okay, now how will you find out the coefficients? So the coefficients will be evaluated by this formula. A naught is given by 1 by t, being the period of the periodic signal. Okay, so integral over one period from t to t plus capital T, where capital T is the period, x of t dt. So this is the formula to find out the DC value. Okay, DC value means average value of your signal. So the first A naught will be obtained by this formula, and then AL will be given by 2 by t integral over one period x of t into cos n omega naught t dt. Okay, so as cos waveform is a even symmetric even signal, you call these coefficients as even coefficients, and then Bn is given by 2 by t integral over one period x of t sin n omega naught t dt. These are called as odd coefficients. Okay, now you can note down the following things. A naught is 0, that is the DC component will be 0 if the signal is symmetric with respect to x-axis, that is with respect to your t-axis, time axis. Okay, so if the signal is symmetric above and below, then the average value will be 0, and then an will be 0 if the signal is odd. If the signal is an odd signal, even coefficients will be 0, and if the signal is an even signal, odd coefficients will be 0. Okay, so you can just see, examine your signal and check whether you will be having all the components or you will be having few coefficients and so on. Okay, and another form of Fourier series is called as exponential Fourier series, and exponential Fourier series is more simpler. You will have instead of sine wave and cosine wave, you will have a complex exponential term. Okay, so the exponential Fourier series is another form of Fourier series using Euler's identity. Here the periodic signal x of t is expressed as x of t is equal to summation n is equal to minus infinity to plus infinity. Okay, from minus infinity plus infinity cn e power j n omega naught t. So this complex exponential will include cosine term and sine term. And how will you find out the coefficient cn? Cn will be given by 1 by t integral over one period x of t into e power minus j n omega naught t. Okay, and excuse me, and then C naught will be given by 1 by t integral over one period x of t dt. Okay, okay, here dt is missing, sorry. Okay, and in this PPT I'll add this also, Parseval's theorem for Fourier series. So this is an important theorem, Parseval's theorem, which will give you the average power of the periodic signal. So you know that periodic signals are power signals. Okay, so the average power, this is the actual formula by which you will find it out in the time domain, and if you have written it in terms of Fourier series, you will have the coefficient Ck. If you take the mod of that and square, okay, or if you square all the coefficients and sum them, it will be getting the power. Okay. Now let us see some examples. This PDF I will be uploading. You can refer to this PDF. Okay, and first let us see the exponential Fourier series. So here instead of here I have used AK instead of C. So this uses the Euler's identity. Euler's identity. So e power j omega naught t is given by cos omega naught t plus j sin omega naught t. So this you all know, you remember this, and this is the Fourier series. Okay, so here we call it as AK. There we call it as C in the PPT. Now it is AK. Both as both the same. Okay. Now instead of K is the variable here. Instead of N, I am having K here. Okay. Okay. Now this first problem is from OpenM, your textbook. Okay. So this is a very simple. All these problems are very simple. Now what is given? Consider a periodic signal x of t with the fundamental period frequency 2 pi. Okay, omega naught is equal to 2 pi, and that is expressed in the form of x of t is equal to k is equal to minus 3 to plus 3 ak into e power j k 2 pi t. Okay, now it is having how many times from minus 3 to plus 3? So you will be having what is it, 3 plus 3 plus 1 for k is equal to 0. So 7 times are there in your Fourier series. Other terms are 0. That means other terms are 0. And it is given a naught is equal to 1, a1 and a minus 1 is 1 by 4, a2 and a of minus 2. The coefficient values is half, and this coefficient a3 and a of minus 3 is 1 by 3. Okay. There is one important here tip. Okay, the tip is this Fourier coefficients will be symmetric. For exponential Fourier series, you will have Fourier coefficients on either side. That is for k is equal to plus or minus what is it, 1 2 3 etc. That is from k is equal to minus infinity to plus infinity. You have the coefficients. So these coefficients will be symmetric. They will be equal on either side. Okay, so that you can remember. If you are given one, you can find out the other and so on. Okay, now it is given omega naught is equal to 2 pi. Now just expanding this from the given expression. Okay, so k is equal to minus 3, so a of minus 3 and e power j k is minus 3, so it will become minus 6 pi into t. Okay, similarly we have expanded all the terms and you are having 7 terms. Now you can you have the values of the coefficients. Substituting the values of the coefficients, okay, you can couple these terms. So 1 by 4 is for 1 by 4 1 by 4 is for f1 and minus 1. So you were having these two terms together, 1 by 2 into these two terms together, these two terms together. Now using Euler's identity, e power j theta plus e power minus j theta by 2 is equal to cos omega naught t. Okay, so now you are having this, so each term will become 2 cos omega naught t. Okay, so now you can write this as 1 plus 2 cos omega cos 2 pi omega naught t. Here already you have 4, so 2 into it in so it becomes 1 by 2. Similarly here you have 2, that 2 got cancelled, so you are having cos 4 pi t, and then here you have 3, so 2 by 3 cos 6 pi t. So this is your signal. Identify the signal. So this is a linear combination of harmonically related sinusoidal signal. Okay, so it is given in the form of Fourier series. Now you have got the actual signal. This is the actual signal. You have synthesized the signal. This is what is asked. So you have finished your sum. Okay, now example 2 is very simple. A single term cos sin omega naught t. So there is only one frequency. There is not much, no more frequencies. Now you find out the Fourier series coefficients. Now we are talking about the exponential Fourier series. So just write this in the form of exponential and terms, complex exponentials. So e power j omega naught t minus e power minus j omega naught t by 2j. This is the formula for sin omega naught t. So now you separate it. So 1 by 2j into e power j omega naught t, and then minus 1 by 2j into e power minus j omega naught t. Now sin omega naught t. So omega naught is your frequency, right? So omega naught is omega naught. What is left is k. The value of k is 1 here and the value of k is minus 1 here. Okay, okay, so f is equal to omega naught. So a1 is equal to, this is here k is equal to 1 and here k is equal to minus 1. So this is equal to 1 by 2j and this is equal to minus 1 by 2j. Okay, now here you are having a what is it, imaginary part. So if you are having an imaginary part, it will be the complex conjugate. The corresponding coefficients will be complex conjugate of each other. If you don't have imaginary part, they will be equal. Okay, that is the real part will be equal and the imaginary part will be the conjugate. Okay, and a naught is not there and ak is equal to 0 for other values of k. So this is you have found out the Fourier series coefficient. A1 and a of minus 1 is there. For other things it is just 0. Okay, now let us come to the next problem. X of t is equal to, you are having 1 plus sine omega naught t cos 2 cos omega naught t plus cos 2 omega naught t plus pi by 4. Find out the Fourier series coefficient. So you have to write this as complex exponential and identify the coefficients, which coefficients are present and which coefficients are not present. So now if it is given in the exponential form, convert it into a sinusoidal signal. If it is in the sinusoidal form, convert it into the exponential form. Use Euler's identity. Okay, so Euler's theorem. So 1 plus 1 by 2j sine omega naught t is e power j omega naught t minus e power minus j omega naught t by 2j. Okay, similarly cos is 1 by 2, so 2 and 2 get cancelled, you get this, and then this cos is again 1 by 2 into this. Here you are having 2 omega naught t plus pi by 4. There is a phase that has to be included here. Okay, now now you take the individual terms. So this is your Fourier series representation, general representation. You have to compare this form with this form, whatever you have got here, and identify the coefficients. Okay, now without any exponential term, here 1 is there, so that is a naught. So a naught is equal to 1, which is called as the DC component, and then a1. Okay, so a1, how will you identify a1? Omega naught is omega naught. Okay, and then a1 is, where do you have 1? E power j omega naught t. Here k is equal to 1 and here also k is equal to 1. Okay, so you are having this plus this, so taking this common, it will be 1 plus 1 by 2j. Okay, here one term is there, here one term is there, so here it is 1 time and here it is 1 by 2j time. So you are having a1 as 1 plus 2j. Okay, it is equal to 1 minus j by 2. Okay, multiplying and dividing by j, so you get 1 minus 2j. And you can find out the mod, because spectrum, what is it, plotting the spectrum we are going to teach in this problem. So mod of a1 will be root of a square plus b square, real part square plus imaginary part square. So you are getting 5 by 4, root 5 divided by 2. Similarly, a of minus 1 is 1 minus 2j and it is equal to 1 plus j by 2, and then mod value you will again get the same thing. Okay, root of 5 by 2. So a1 and a minus 1, the mod value will be the same, but the angle will be different, the phase will be different. Okay, now identify a2. A2 you are having half into e power j pi by 4. Okay, how? Here you have e power j 2 omega naught t. So here it is k is equal to 2 and you have what is it, into e power pi by 4. Okay, so e power pi by 4 is extra, so it will come here. So 1 by 2 into e power pi by 4 is the coefficient of this term, e power j omega 2 omega naught t. For this, the coefficient is e power pi by 4 into half. Okay, so that's why you are having a of 2 is equal to half into e power j pi by 4. So you can write this as cos pi by 4 plus j sin pi by 4. It is equal to 1 by 2 into 1 by root 2 plus j by root 2. Okay, so when you get this, and then a2 is equal to this, and then mod of a2, okay, you have to find out. And similarly, a of minus 2 is equal to 1 minus j, and mod of that you have to find out. Okay, so now if you find out the magnitude spectrum, here we have found out the magnitude, so you can plot the magnitude with respect to k. Okay, for k is the coefficient number, it is the number. So for 0 it is 1, and for 1 and minus 1 it is root 2 by 2, and here it is half. For 2 and plus 2 and minus 2 it is half, and ak is equal to 0 for other values of k. For mod of k greater than 0 it is 0. So you have plotted the spectrum. This means for the what is it the dc value for frequency equal to 0, its magnitude is 1. For frequency is equal to omega naught, its magnitude is what is it this plus this, and for frequency is equal to omega naught, you are having this is the magnitude, and the magnitude spectrum will be symmetric. Okay. Similarly, you can find out the phase spectrum. It will be antisymmetric. Angle of A1 will be tan inverse of B by A. So tan inverse of what is it minus 1 by 2. So it is minus 26.5. When you find out for A of minus 1, it is tan inverse of 1 by 2. So it is plus 26.5. Similarly, A2 you are getting 45. For A of minus 2, it is minus 45. A of 0 is equal to 0 because you don't have any what is it imaginary part there. Okay, so now you get for minus 1 minus 25 plus 1, here it is plus 26, and then plus 45 minus 45. So this spectrum will be antisymmetric. Okay. Okay, and then similar example, find the Fourier series of the signal. Also find the power of the signal using Fourier coefficients. So I am leaving this to read and understood by you. Here the signal is a combination of two signals. What they are doing, they are finding out omega naught. Okay, and then T. Okay, you can understand very easily. Finally, what I want to tell you is after finding the coefficients, okay, you are getting the coefficients, and to get power you have to use the Parseval's theorem. Parseval's theorem says that the power can be obtained by summating okay, the square of the coefficients, square of the Fourier series coefficients. Very simple. So summation k is equal to minus infinity plus infinity mod of ak the whole square will give you the power. So you are having what is it 5 coefficients here, and you just what is square them and add them, you will get the power. Okay, so simple to get the power. Okay, and then one more example for exponential Fourier series given a signal diagram graphically. Okay, graphical signal. There is a periodic signal, and for this find out the Fourier series using what is it the formula. So first you have to find out the period. Period is it starts here, and the next what is it? It again repeats here. Okay, so 0 to 4. You have to be careful in finding out your period. It is not to from here to here. The period is from till here. You are having some what is it values. Here you don't have values, but it repeats at 4. So the period is 4. So if t is equal to 4, omega naught will be 2 pi by t. So it will be 2 pi by 4, it is pi by 2. Okay. And now the formula a naught is equal to 1 by t, x of t, integral x of t dt. So on seeing the signal of t is 4, and then integral x of t is having two different values. From 0 to 1 it is 2, and from 1 to 2 it is 1. Okay. So integral is given as two terms, from 0 to 1, 2 into dt, and plus 1 to 2 it is 1 into dt. Okay, so now when you apply, you are getting 3 by 4. 3 by 4 as your answer. Okay, similarly ak excuse me. So ak can be obtained by 1 by t integral 0 to t x of t e power minus j k omega naught t. So omega naught you have found it as pi by 2. So you substitute pi by 2, and then from 0 to 1, from 1 to 2 you are having different values. So now you have two terms of integration. After integration, apply the limits. Okay, and you are getting these terms. Okay, these terms, and here this and this. Okay, here you have minus 1 minus e power j k pi by 2, and here plus half e power j minus j pi by 2. Sorry, minus is missing here. I have a minus here. So when you combine these two, it becomes minus half e power jk by 2. Okay. So the final answer is you have three terms. Okay, 1 minus 1 by 2 e power minus jk pi by 2. And then, okay, this term is changed as minus 1 power n. Okay, that is half into e power j k pi. So this depends on the value of k. So minus 1 power n. Okay, let us finish with one more example in trigonometric Fourier series. Trigonometric Fourier series, already I have given you the formula in the PPT. Okay, and again I am writing it again. You have a naught, an, bn as the coefficients. An terms are the coefficients of cosine terms, bn are the coefficients of sine terms. Okay, and you have to find out all the three using this formula, 1 by t naught, 0 to t naught, and this formula you have to use. Okay, so study the formula and then you will anyway, it is an open book, you can easily refer to the formula also. Okay, now see this example. Find the trigonometric Fourier series of the following signal. What is this? It's the square wave. Okay. Okay. So this one, for this waveform. So again, first find out the period. So if it starts here, if you say that it starts here, it goes from -1 to +1, and then it is negative for 2 more cycles. Okay, so it is here, it is 1 2 3 4, t is equal to 4, time period is equal to 4. From this waveform you can find that t is equal to 4 and omega naught is equal to pi by 2, 2 pi by t, so it is pi by 2. Okay, and now you can see this. Analyze the signal first. So this signal is what is it? It is symmetric with respect to the x-axis. Okay, that is here. Upper side the amplitude goes up to +1, and then on the other side it goes up to -1. So it is symmetric with respect to the t-axis. So the average value a naught will be 0. As it is symmetric with respect to the x-axis, its average value will be 0. A naught is 0. And then you have to check whether it is an even signal, pure even signal or odd signal. Okay. Now you can see that it is a pure even signal. So its odd component will be 0. So what is the odd component? Bn is the odd component. So Bn will also be 0. So this signal is symmetrical. Okay. Hence Bn will also be 0. A naught is also 0. So you need to find out only An. Okay. So now find out An. So 2 by t naught -1 to 3 x of t into cos n omega naught t is the formula. Okay, substitute 2 by 4, and then again you have two values, so split the integral into 2. -1 to 1, the value is 1 cos n pi by 2 t dt, and then here it is -1 from 1 to 3, it is -1, so cos n pi by 2, excuse me, to dt. Okay, so when you integrate, you are getting sin n pi by 2 into t divided by n pi by 2. Okay, so you get this 2 here, similarly you get this 2 here, and overall you are having a half that will get cancelled. Okay, so now you have to substitute the limits and find out this 2 has got cancelled and you are having n pi in the denominator, so 1 by n pi is taken out and you are having 4 times now. So sin n pi by 2 minus n pi by 2 minus sin 3 n pi by 2 plus sin n pi by 2. Okay, so now if you see, this is n pi by 2, and then this is a what is it, odd signal, so you get minus of minus, so it will be plus sin n pi by 2. Yeah, okay, it is an odd signal, so you get plus minus of minus, it will be plus, and then here also this becomes plus 3 pi n by 2. So you seeing the symmetric property of sine waveform, it is again sin n pi by 4 by 2 and plus sine n pi by 2. Okay, so you are getting 4 sine n pi by 2 divided by n pi. Okay, so an value is this, and now again, if an is 0 for n is equal to even, so now if n is equal to 2, it will be sine pi. Okay, sine if n is equal to 4, it will be sine 2 pi and so on. So sine pi, sine 2 pi, sine 4 pi, everything will be 0. So an will be 0 again for n is equal to even. And then if n is equal to 1, what will happen? If n is equal to 1, it will be 1. And if n is equal to 3, it will be 3 pi by 2, so it will be minus 1. Okay, and for n is equal to 5, it will be again plus 1. For n is equal to 7, it will be minus 1 and so on. So again you can generalize it as an will be equal to 4 n pi n pi. For n is equal to, this term will become plus 1 for these values of n, and this will become minus 1 for these values of n. Okay, now what you can do is 4 by okay, n you have to substitute. So 4 by pi is taken out, and then for n is equal to 0, the term is 0, and for n is equal to 1, it will be here is your original what is it? Original equation. X of t is equal to a naught plus summation an cos omega naught nt. This term is 0, this term is 0. So for n is equal to 1, it will be a1 into cos omega naught t. Okay, and for n is equal to 2, the value becomes 0. For n is equal to 3, it becomes a3 cos 3 omega naught t. Okay, so that's what we have written is the last statement. So cos pi by 2t, and for the next value it will become minus. Okay, so minus 1 by 3. Okay, 4 by pi is taken out, and minus 1 by n. So 1 by 3 cos 3 pi by 2t, plus for 5 it will be plus, so it will be 1 by 5 cos 5 pi by 2 into t, and for 7 it will be minus, so minus 1 by 7 cos. So this is the Fourier series expression of the given square wave signal. Okay, okay, I hope you all have understood. Okay, so you can take it as a reference, and you may be able to solve the other possible problems. Okay, all the best. Bye.